Hello and welcome back to Chapter 1.7 from Stevens' Matrices, Vectors, and 3D Math. This is the second video from this particular section, and we are dealing with matrix transformations. When we say a matrix transformation, it means we're starting with an initial point in 2 space or 3 space. We're multiplying on the left by a transformation matrix of some type, and that gives me a new point in 2 space or 3 space. Right? So that's what I mean by matrix transformation. You're multiplying on the left by this matrix, and you hit every point of your 2 or 3D object with this matrix multiplication. The great thing about this is if you have a whole sequence of operations you can do, you can multiply all of the matrices together to create one single matrix transformation that does what you want. And likewise, if t gives you the transformation to a new point or new vector, t inverse, when you apply it to the new vector, will get you back to the original one. So you go back and forth. Let's see, then we did some transformation matrices. We did a scaling matrix, a rotation matrix. Alright, we did 2 reflections, actually 3. This was a reflection across a line. And then we did translations, but we did matrix form and non-matrix form. And in this case we were just taking a point and moving it delta x in the x directions, delta y in the y direction, getting a new point. That's the change in x, change in y. You can do that with a matrix multiplication, where you bump up the dimension by 1. Or you can just take your x's and y's and add delta x and delta y. Then we talked about some horizontal shearing, some vertical shearing, and the properties that these matrix transformations had. We did a little demonstration with the house. First we rotated it 60 degrees, then we reflected that across the y-axis, and then we translated 1 unit to the right, 2 units up. And this was done with straight up matrix multiplication on the left. Those are our transformation matrices there and there. And when we did the translation, we didn't use the matrix translation, we just added dx and dy. And the MATLAB code for this, there is sort of a sequence of events. Right, so there is, say, the first rotation matrix. Then in the next line, I put the x values from the house and the y values for the house in a single matrix of points separated by a semicolon, which made it look like this: x1, y1, x2, y2, on and on and on. So I was able to hit every point of the house with a single multiplication. But what that does return is a similar shaped, the same shaped matrix that have the x and y values in one matrix. So if I want the x values, I first strip those out of the x and y values, call those x values. Then I get the second row, call those the y values, and that is what is needed to do the plotting. So that was the rotation. And then the exact same process was used for the reflection, where that was my reflection matrix T2. And then my translation matrix was just taking all of the x values and adding dx, which was 1, and then all of the y values and adding dy, which was 2, and that moved my house 1 unit to the right and 2 up. Then we talked about rotating around things other than the origin. Right, rotating around the origin was straightforward use of that rotation matrix, but if I wanted to rotate around, say, a point like A, then the first thing I would do is subtract A from all the points. That would put A at the origin, B would be down here, C would be down here, and then I would rotate this around the origin by 90 degrees, but then I would translate everything back up by A. And it would produce the rotation around the point A. And so that's how you do a rotation around another point. First you subtract the point, then you do the rotation, then you add the point back on. All right, and so all of this stuff leads us into this one demonstration I wanted to do. That's why there's actually two parts to this chapter. This little animation. In this animation we have a guy or a character, which is just this ellipse. It's going to go down this hill. And when it gets about halfway, it's going to fall and start rotating clockwise as it falls down the hill. All right. Okay. So it's a simple game plan. The game plan is I'm going to create this hill. All right. And then I'm going to create my ellipse. And basically I'm just going to translate my ellipse by dx and dy, letting it follow this path until it gets to a certain height, and then I'm going to rotate and translate. Remember, I have to rotate first and then translate. Alright, so your guy really starts here, and you'll rotate here and move. Rotate a little more, move. Rotate a little more and move. Keep in mind, if you move first and then rotate, suppose your guy originally starts here. If you move him here first and then rotate this ellipse around the origin, it will go like over here. So that's not what you want. So you need to rotate first, translate second. Okay, so the first thing I'm going to do is just create my hill and my character. The hill looks just like negative x squared. Alright, which looks like this, but I don't need the left-hand part of that. And I need to bump this right half of the parabola up by 100, but then that just makes it too big, so I multiply that by 0.2. And so I have a parabola that starts when x equals 0 at 0.2 times 100, so my parabola is starting here at y equals 20 for x equals 0. And then when x equals 10, this is 0 and my y is 0. So that created this parabola. And my character, my guy, is just an ellipse that is taller, so has an x radius of 1 and a y radius of 2. So he's taller than he is wide, right? And you have to let t go from 0 to 2 pi so that you get the entire ellipse in there. Right now that ellipse is centered at 0, 0. We'll worry about moving or translating this ellipse later. Right? Okay, so first thing we'll do is we'll create a function. We have our function capital F, and this is what defines the hill. This defines the hill, right? And so I'll put in a dx value into my anonymous function, and that'll produce dy, which is just my position, right? So I'm just going to move the guy along the trajectory with dx and dy defined using this function. And when the guy gets halfway down, I'm going to start rotating him before I translate him. And remember, we must rotate him before the translation, otherwise the translated guy will rotate around the origin, and that's not at all what you want. You might do it that way, you'll notice right away that something is strange. This linspace command is just to create a vector of x values that I use to create the hill. It's a very handy command to have. For example, if you have linspace 0, 6 to 1, that'll give you 6 points starting at 0, ending at 1. So you actually get 0, 0.2, 0.4, 0.6, 0.8, and 1. So it's a really handy way to get the desired number of points that start and end. You know, you could build a vector like this, but this linspace does it automatically for you. Very handy. You want to give each graph a name so that you can delete it and then redraw it for the animation to look real. And you can insert a pause time that's greater or less than the one in this example. So here's the code. It is called wipeout.m. It is in the program repository. I'll go through it briefly. This is the hill. This is the function that gives the y values. So there's my x values. That's using that linspace. So I'm going from 0 to 10, and there's going to be 200 x values. And I'm actually going to proceed down these x values, so they're going to be actually 200 frames in my movie. And then y hill is just going to be f of x hill. So my x hill and y hill will create that red hill. My original guy located at 0, 0. I first create the parameter t, goes from 0 to 2 pi. X values are cosine t. The x radius is 1. Y guy, 2 times the sine, so the y radius is 2. That makes him taller than he is wide. Then I do my original plot. This is just the hill plot. I want to use axis equal and hold on so that my animation, so I'm not redrawing these pictures. If you don't put hold on, you'll notice it because it just redraws everything. It looks crazy. And axis equal makes sure my ellipse looks like an ellipse and my rotations look as they should. And this is a graph of the guy, but notice the x guys are the same x's associated with my ellipse, but the y values are bumped up by 20. So that takes my guy, which starts here, and moves him up to there, which was the top of the hill. So that's my original guy is at the top of that hill. Wait for button press, waits for someone to click on the figure, and that'll start the animation. Before I start the animation, I initialize my value of theta. That's the rotation. It is 0. It will remain 0 until this character gets halfway down the hill. So dx is just my x values. That's going to go from 0 by 0.1 to 10. So that's going to go 0, 0.1, 0.2. So actually in this particular case, let's see, 10 times 10. I'm only doing 100 frames in this particular animation. And then dy is just going to be f of dx. So this creates my hill right here. And now, so I've already have my guy plot. So I'm going to delete that guy plot, and then this is going to be my redrawing. If my height, my dy, if that's greater than 10, all I'm taking is my x guy and my y guys, right? That's those ellipses, and I'm adding dx and dy. So that takes my ellipse, which is starting here, and moving it to somewhere on the hill, right? Every time until I get down to 10. Alright, so this is just that translation that we talked about on the first video from this section. If dy is not greater than 10, that means dy is less than or equal to 10, means I'm down here. Alright? Okay, and so if that's the case, I'm going to increment theta by pi over 8. That means that this character will get rotated by theta. Whatever it is, it'll keep rotating by pi over 8. So there's my rotation matrix, right? And then I'm going to rotate the guy. There it is, the rotation matrix times x guy, y guy. That's the original guy centered at the origin in the vertical position, right? And theta is what's going to increase every time I pass through this loop. And then what I do is I peel off, so here I do the rotation, here I peel off the x values, y values suitable for plotting. But notice, I don't just plot the x and y values. After I've rotated, I now add dx to my x's, I rotate, I add dy to my y's. And so I'm rotating first, then translating. And that's my new guy plot. I do a little pause, make sure I keep my axis bounds where they were the whole time so the screen doesn't shake around. And I loop back up around, right? Until I get to x is 10. That's when I stop. Alright, so that wraps it up. I recommend that you go grab this code and just run it and play around with it. You can change how fast it goes, what the ellipse looks like. You should take a notice that if you change this pi over 8 to something smaller, the rotation will actually go slower. If you make it bigger, it'll appear to rotate faster, but it might be sort of choppy. So feel free to grab it, play around, and then do the homework. So that wraps up chapter 1.7. I will see you in the next chapter. All right, bye.